Swayam Prabha. Digital India. Educated India.
So, welcome back. We will continue with our exploration of Laplacian spectrum. So, in the morning we saw about matrix tree theorem and the number of spanning forests. Right? Now, we will get back to what we were doing yesterday about the largest eigenvalue or largest spectral value of Laplacian, and we will try to give some bounds. Okay? So, today our target will be to find bounds. For lambda 1, for which lambda 1? Of course, we are talking in terms of Laplacian spectrum. So, lambda 1 of the Laplacian spectrum, right. And then we will also talk about the second smallest eigenvalue, right, the algebraic connectivity. We will also try to see what kind of values it can take. Okay. So, what do you expect the largest eigenvalue to take values? What should it be? How far can we go? So, we are talking about lambda 1. So, that means we have already considering the arrangement lambda 1 is greater than or equal to lambda 2, and we know at least lambda n is equal to 0, right. So, this much we know. So, the question is, what can the value of lambda 1 be, or what is the range that we can think of where lambda 1 will lie in, will be lying. So, you have seen some examples already. So, what are the values that we have seen? At most 2e. So, one answer I get is less than or equal to 2 times e. E is number of edges. Okay. So, let me write this way. So, we have seen some Laplacian spectrum, right, some values, at least for some classes of graphs we have seen. So, from there what can you conclude? I mean, do you get some feel for what can be the values? The largest spectral value at most n. Okay. So, obviously, we should be expecting all these, right. Obviously, twice number of edges is a very big number when you have a dense graph, at least as long as you have a minimum connected graph, we should be seeing that this is going to be a bigger number, right. So, okay, we have got some answers for upper bound. What do you think would be the lower bound for the largest eigenvalue? We are not talking about other eigenvalues. I mean, we concentrate only on the largest eigenvalue. So, what do you think it could be? 0 is one trivial option. So, when can lambda 1 be 0? Only for disconnected graph? Lambda 1 I am talking about largest eigenvalue. So, when lambda 1 equal to 0 means what? You know lambda n is 0 and they are all in decreasing order. So, that means what? All the eigenvalues are 0. So, when can that happen? So, if you have an isolated graph, right, every vertex has degree 0, right, or there is no edge in the graph. So, that is a very trivial case. So, let us not worry about that part now. So, let us assume that we have at least one edge in the graph. If we have at least one edge, then this turns out, we will not have this option. So, lambda 1 equal to 0 means that my edge set of G is empty. So, what are the other possible bounds for the largest eigenvalue? So, let me give you this result, but the proof is a little bit involved, and you should be, I mean, we will be using Cauchy-Schwarz inequality and other results to prove the bounds. So, the lower bound for lambda 1, I mean, roughly you can say that it has to be at least the max degree, right. You have seen already every, I mean, if you have a complete graph, you know what your lambda n is going to, lambda 1 is going to be, right. So, this is delta is one trivial bound. This is the lambda 1, the largest eigenvalue is at least delta. Okay. In fact, there is a tighter bound also, we can think of delta plus 1. In case of complete graph, it is equal, right? Delta plus 1 is nothing but equal to n. So, that is what you get, the largest eigenvalue is equal to n, right, in case of complete graph. So, this is a tight bound, delta plus 1 is a tight lower bound that we can have. So, what can we say about the other end? The other end, there are people are still improvising the upper bound. Okay. So, we will start from roughly we can say that n is one possibility. Okay. In terms of delta, we can also have another possibility, which would be 2 times delta. So, your largest eigenvalue lies between delta and 2 delta, okay, twice, it cannot go beyond that. Okay. So, that is the idea here. So, let us try to prove this upper bound, because lower bound is kind of trivial, you can just prove it using the basic definition of lambda and you can just get it done with. Okay. So, to prove the first upper bound, let me state another result. Okay. So, if all the statements go together, so if we have G is a, say let us talk about connected graph, even for disconnected it holds good, only that because we are talking about largest graph, connected graph on n vertices. So, let lambda 1 be, I should not say let. So, then the largest Laplacian eigenvalue lambda 1 is bounded by maximum over d I plus d j minus C of I j for what kind of I and j? 1 less than I, not equal to j, and let us in fact take I is strictly less than j, and maximum is taken over all adjacent pairs. So, we will start proving this. From here the other result will follow immediately. So, how do we prove this? So, let us catch hold of the eigenvector which is going to be associated with the lambda 1. So, let x be the eigenvector of lambda 1. So, that means what? Okay, let me also give a very specific representation, x equal to x1 x2 xn, right, the vector x1 x2 xn. So, what does this, how does this translate to? We have Lx is equal to lambda 1 times x, right. I mean this is what we have been doing when we try to prove something, we take the basic definition and from there we go. So, Lx equal to lambda 1 x we have. So, what does this give? If we have an n by n matrix, we will be having n by n equations, right. If I expand this Lx equal to lambda 1 x, we have n equations to handle, right. So, let us catch hold of those equations. So, from this vector, let me just pick out two of the values for xi. Okay, from this vector x, let me just pick out 2 values, we will talk about that, that would give us the bound. Okay. So, the first one, let I be one element from this vector which is going to be the maximum over all xi's. Okay. So, since we are talking about lambda 1, obviously not all ones we are going to have. So, that is one ruled out option. Similarly, let us look at the minimum vector, the value of the component being minimum. Okay. So, minimum over all x k's, let me just rewrite this. within the vector, right. Within the eigenvector I am just choosing the minimum and maximum, so that I will capture those two vertices or that row, so that we can talk about those two rows here in this set of equations. So, now we have n equations, right, if I expand Lx. So, if we expand it, what do we get? Say let me look at the ith row of this expansion. What do we have? The right hand side would be nothing but lambda 1 into xi, right. So, if you write it in the vector form, you have this matrix, you have x1, x2, xn, this is going to be equal to lambda 1 times x1 to xn. So, in this we are going to, we have n equations, right. If we expand this, we will get n equation. Now, look at that ith equation, where the I is coming from this xi, the corresponding xi component. Let us look into it. So, what will be the equation? If I expand this equation, how will the expression be? We are looking at the ith row here. Right, ith row you just take and multiply it with this column, you get the ith element of this vector, right. So, what will be that? So, one side you have lambda 1 into xi, the right hand side, I will just write it this side. What would be the other one? This side you will have minus 1 zeros, x1, x2, everything will be there, right. But the diagonal entry will be always existing, right. So, that would be nothing but di xi, that is a positive entry that is going to exist, and you will also have wherever there is an edge between I and the other nodes, those xi's will only exist. In other places it is going to be 0, right. It is like minus 1 into all those positions where my I is adjacent to, I mean all those neighbors of I will capture. So, let me just write this as sigma xk, where k is adjacent to I. Okay. So, similarly, if I write the equation for the jth x, let us capture the jth row for where the j is nothing but that vector which gives me the, I mean that row which is going to give me the minimum x value, right. So, that would be nothing but lambda 1 xj, which is equal to di dj xj minus all those k adjacent to j and summation over xk, right. So, now this equation I can also look at this summation part, because if you see here, what did I say about the Cij? Now, let me just split this summation. Okay. Look at this k vertex. Now, we know all those vertices which are adjacent to I, right. So, now I can look at these neighbors in two sets, like if I have this vertex I know all these k's which are going to be adjacent, right. All these are going to be my xk which would be contributing to this sum, right. So, from here I will divide the sum into two parts, that would be useful for me in such a way that all those vertices which are also going to be adjacent to the vertex j. Okay, my j is, I mean I am talking about I and j, two vertices. So, let me capture all those things, so that these set of vertices which are adjacent to j and these set of vertices which are not adjacent to j. Okay, so, if we split this sum, this would be nothing but di xi minus sigma k is adjacent to I and k is adjacent to j xk minus sigma k is adjacent to I and k is not adjacent to j xk, right. I have just pulled it out separately, right. Similarly, from j also I can take the same stand, right. I can just look at j's neighbors, whatever is there in common with I will separate it out, right, because we are kind of going to do a double count on this. So, let me just pull it out. So, this would be nothing but dj xj minus sigma k is adjacent to j and k is adjacent to I xk minus sigma k is adjacent to j and k is not adjacent to I. Are we talking about j here? Yeah, sorry. Yes, k is not adjacent to I xk, right. So, now from these two equations I just want to pull out the common factors that could be taken out. So, let us look at the equations, say this is say 1 and this would be 2 the later part, I just pull it out. So, let us look at the difference of these two equations. Okay, somewhere I need to connect the commonality here. So, let us just pull it out. So, what do we get? So, lambda 1 into x I minus x j is equal to d I x I minus d j x j minus all those vertices which are common to I and j, right. There is one part here, this second sum over here in equation 1, this tells all those vertices which are adjacent to I and j, right. Here also we have the second sum which is going to be adjacent to I and j, right. So, let us just rewrite that part. So, there is a double count here, I can just see this. So, all those vertices adjacent to I and j, and you have the remaining vertices, right. So, how many will be there here in this sum, how much will be contributed? I just asked how many terms are going to be there here, because we are talking about upper bound, I am just trying to pull out the terms, right. We know x k is going to be smaller, right, than x I, because x I is my largest term and x j is my smallest term, right. So, how many terms are going to be there here? Here I have just split this term, right. So, this total sum, the second sum over here, k adjacent to I, how many terms are going to be there in that sum? If I have my matrix, right, I am just looking at all those vertices which are adjacent to my ith vertex, right. So, how many vertices are going to be there? Degree of I, right. So, this sum contains actually degree of I terms. From that I am trying to pull out all those vertices which are common to j, right, and this is going to be remaining terms here, right. So, that would be d I minus the common neighbors, right, whatever is there. So, so that is what I am trying to do here. So, this term would be nothing but, so let me just rewrite this, let me give the count for this. This 2 times summation I can just give an upper bound here. So, we are going to jump from equality to bound. So, this would be d I minus of the number of common terms, right, common between I and j. This C I j is that term. The C I j in the previous expression, that what I asked is nothing but number of common neighbors of I and j. Okay. So, if you just simplify this, putting in all the required expressions, if you just simplify it, we will get an expression looking like this: lambda 1 times x I minus x j is equal to d I plus d j minus C of I j, number of common terms, right, into x I minus x j, okay. And this is going to be less than or equal to. So, I have just introduced the inequality here, in fact it would be equal, right. I am just rewriting them everything here in terms of just the degrees, right. D I x j would be introduced over here, because there is a negative sign, I can approximate this by the minimum x j, I can just pull it out and I can just write it in this fashion, right. So, from this what can I conclude? The argument here is, since we know we are lambda 1 is not the eigenvalue of 0 vector, so x I is not equal to x j for every possible I equal to j, right, because we have taken an arbitrary argument here, and lambda 1 is not equal to 0, the 0 eigenvalue, because we know only for 0 eigenvalue we have every component being equal in the eigenvector, right. Since that is not the case, we can say that x I is not equal to x j, and therefore, I can just conclude that, oh, I said there is an inequality here. So, lambda 1 is less than or equal to d I plus d j minus C of I j. So, here we can just look at, since it is a less than or equal to, when I vary this over all I and j, right, I can just see that I will get the maximum over. So, this would be less than or equal to all, when I do the maximum over all I and j, we get d I plus d j minus C of I j. So, now we know what C of I j is, number of common neighbors between I and j. So, now we can see that this upper bound is like if there is no common neighbors, this is still in the negative term. If every vertex has a common neighbor, then it would be like a complete graph, right? That is not going to be the possibility. So, we can immediately see from here that this inequality is still further improved. You could say it is nothing but maximum over di plus dj. Right. Cij could be 0 also, right? That is the worst case. So, in the worst case possibility is maximum over di plus dj. So, what will be this combination? Maximum over di plus dj. Worst case scenario is when you have di dj both are maximum degree, right? D max if we have, then this would become, this is less than or equal to d max plus d max, which would be twice delta, right. So, this is one of the bounds that we started here. Lambda 1 is less than or equal to 2 lambda, 2 times maximum degree, right. So, this is one result. There are also further improvements on this you will be seeing. Can you tell me where this is attained? Have we seen any class where this is attained? We have seen a class, at least one class of graph where this upper bound is attained. We only seen 3 classes, we did not see more than that, right. What are the classes? Complete graph, complete bipartite graph, and cycles. Did we see cycles? I think not. And we also saw some kn minus p when you delete p edges, right.